The oxygen is what? -2 each. Now, this is going to be our first time we've seen this. So that means we have 6 negative charges, but the overall ion has a net charge of -2. Therefore, the carbon has to be +4. Look at you guys go. Okay. Because I know. Now, over here, are there any that we know? The hydrogen is going to be +1. The only time hydrogen is going to be a -1 is if it's combined with a metal. And just a metal. Clearly, nitrogen is not a metal. So, each of the hydrogens is +1 each. The overall ion has to have a net charge of +1, so the nitrogen is going to have to be -3. All right. You guys are starting to get the hang of things, yes?
Are there only certain ones you know?
Yes.
For sure.
Yes.
Okay, so all the other
Well,
ones are changeable.
yes.
Okay.
But even the ones that we know, for example, oxygen,
Yeah.
but that's kind of a special circumstance.
Yeah.
Thank you, young lady.
And those were in the chart, right?
Yeah. All right. Now would be a good time to try and cut you loose, wouldn't it? All right. See what you can. Now, I actually left you some interesting ones, but do what you can. I guess I haven't done it yet. Yeah. No, I'm going to do it like sometime today. Matt, you good?
Yeah.
All right. Pretty easy, wasn't it?
Yeah.
Getting that water boiling, maybe not so much. Okay, so I learned last year that if I walk away and get out of range of the Bluetooth microphone gets out of range, then the whole video shuts down. So I've learned to take off the microphone. Which means when I walk out of the room and all the things that you say about me while I'm gone, those get recorded. She's like, her eyes lit up. Yes. All right, how are we doing?
The last one you just wanted to...
No. Okay, here we go. Now, this one probably looks kind of complicated. However, is there anything in there that you recognize? The ammonium ion, and probably the phosphate ion, if not the hydrogen phosphate ion. So if you want to look at it as individual ions, in my opinion, that's kind of the way to go. That's how I do it, okay? So with that being said, heck, we already know the ammonium. We already did that one, right? So we've got +1 each here. We know that this is going to be +1. Okay. Over here, we know this is -3. The phosphate, if you want to look at it as phosphate, you can do it that way. What are the oxygens going to be? -2 each, which makes the phosphorus plus 5. Anyone get all of four of those atoms correct?
Question. So we can't like do the whole ammonia thing because like the ammonium up there and the choice is 1 plus. We can't do that though.
Yeah, we can.
So we could use that whole thing.
Because this has a 1 plus.
Yeah.
There's 2 of them.
So we could just say 1 plus for like each of those.
No.
And -3.
No. Because notice how I'm asking the questions. What is the oxidation state of each element? And that I'm being very specific on that. Okay, each element. All right, next. Are there any that we know? Yeah, the oxygens are -1 each this time because this is a peroxide. How many of you got that right? Very good. You will see this again. This is the one that will catch you. Not trick, catch you. You have to be careful. And then lastly, what do we have over here? Any that we know? Oxygens, what are they? -2 each. Therefore,
I don't think that's possible. I think. Listen. This is the knowledge I did. Not right. Alright, listen.
then this would be fake knowledge.
So you remember the flippy thing we did?
The what?
The flippy thing?
I do remember that is a way.
Oxygen was 3. That's not real though, but like I still said it.
Yeah, that's not real.
That's all I got, guys. I mean, it was
Joe may remember this from last year.
2 of the ions are +3 and 1 of the ions is +2.
Yep.
What in the world? I can do that. I know. I remember you mentioned.
Yeah. There you go. This is actually closer to what rust would actually be because actual rust would have a little combination of iron 3 and iron 2. Everybody say hi to Mr. Heffernan when he walks in. Oh, looks like he's going to go the other way. I think he was shocked that first time he came in here. Whoa, what's going on in here? Anyone have any questions? Anyone have any questions? Okay, this is the foundation of everything else we're going to do as far as the rest of Chapter 4, the redox stuff, and then continuing into Chapter 19 when we do the electrochemistry. Okay, this is like converting grams to moles. Okay, here we go. Next. We are going to use this. In fact, Mr. Hummon and I are old enough that this is how we learn to balance equations, what I'm about to show you. Okay? So we can use this idea of changes in oxidation state. Now remember back in, whenever you guys, possibly freshmen, maybe before that, you may or may not have learned that chemical changes are a scenario in which a substance makes new things. Okay? For example, water evaporating is a physical change because it's still water, both from the liquid state to the gaseous state. Whereas burning methane, reacting it with oxygen, CH4 plus oxygen, gives us carbon dioxide and water. There's new things being formed. Well, a change in oxidation state also is a chemical change. Something has changed. Okay. Now, what is going to cause? How is an element, a species, going to change its oxidation state? What's going to happen? Yeah, it's the number of electrons that gets transferred. They're either being added or being taken away. So let's look at this idea, and I think I am going to use the methane as an example here. Oh, I turned away from my example. Yeah, let's do that. So let's combust. A little methane, CH4 plus oxygen yielding carbon dioxide and water. I'm going to introduce some terminology as we're going through this. And we need to start to become very comfortable with the terminology. This is our first example of a redox reaction. If you guys could take a moment and assign oxidation states to each of those elements in each of the compounds. Won't take you long. No, not yet. This is actually where we're headed. This is where we're headed. You were not here yesterday, is that right? Which is why you didn't have that? Okay. I'm not going to grade it. And everybody I thought you grabbed one already. Everyone needs more practice. Okay, are we done? Are there any that we know here? Hydrogen's going to be +1 each, therefore the carbon is -4. Oxygens here are 0. Well, I know. Over here, are there any that we know? Oxygens are -2 each, therefore the carbon is +4. Ooh. No, it's not. Peroxides are going to have a metal. Peroxide ion. Peroxide ion.
Oh, boo. I gotta write that.
Okay. Over here we have. Yeah. Okay, so now here's the way some questions on the AP are going to happen. You're going to need to determine whether a reaction is a redox reaction or not. How do you find out if a reaction is a redox reaction? What you look for is a change in oxidation state for any elements. Do any of the oxidation states change for any elements? The carbon clearly changed its state. It went from -4 to +4. Okay? And the oxygen went from 0 to negative. Now here's the other thing. So is this clearly a redox reaction? Was there a change in oxidation states? Not only will there be if it is redox reaction, will there be a change in oxidation state? One of them is going to become more negative. The other one has to become more positive. You have to have both, because as Joe said earlier, to change oxidation state, you have to transfer electrons. Well, the only way to go from being negative to positive is by losing electrons, and the only way to become more negative is to gain electrons. The electrons are staying within the community here. Okay, you're not getting electrons from an outside source. The electrons aren't going to an outside place. They're all within the system. We call this a system here. And as Chelsea was just asking earlier, we are going to use the number of electrons that get exchanged to help us balance the equation. You didn't know that, but you were headed in that direction. Okay? All right. So, some terminology to be introduced you to. The carbon is said to have become oxidized. So carbon oxidized. And now here's what we're going to do. For those of you that went through this last year, you may remember this. By how many electrons did carbon oxidize? 8. Ooh. Okay? And what species reduced? Each oxygen reduced by 2 electrons. Now there's the terminology. Oxidizing means losing electrons. Reducing means gaining electrons. For those of you that have never been exposed to this, that seems counterintuitive, right, Emily?
No, I went to last year in biology.
Oh, excellent. Okay. What's reducing for these atoms is the charge. It's becoming more negative. For those of you that have never seen this before. So oxidizing means gaining electrons, or sorry about that, losing electrons. Reducing means gaining electrons. There are numerous ways for you to remember that. I am not going to sit there and give you any ideas because I don't want to contaminate anything. I like to, and this is just me, not everybody's the same way, but I like to learn a thing. I don't like to learn a thing to remember a thing. If that makes any sense. Yeah, I'm not a mnemonics kind of guy. But there are a few mnemonics out there if you guys are into that. I believe this book might have 1 or 2 of them. Morgan, you might be able to help me out on that. No. Did you see anything in there? No, she's going to look it up. Well, no, but she has looked at. Yeah. Oh, oil rig or Leo goes grr. Those are the 2. But I'm not even gonna play with them. You guys do that if you want. Yeah.
Oh, yeah.
I don't do that. What's that? 8 electrons.
Yeah.
It went from -2, or sorry, -4 to +4.
Oh, okay.
I'll let you do the math.
Yeah, okay.
Yeah, that's all right. Okay, so now what we are going to do is use the number of electrons to help us balance the equation because, as I said earlier, we're not going to create electrons from some outside source or destroy any electrons by making them go somewhere else. They all have to stay within the system. And that's where we're headed next. I'm trying to think if there's any other terminology. The AP has taken this away. They are no longer testing you on these 2 phrases. However, the rest of your life, you're going to hear these phrases. Have you ever heard of a reducing agent or an oxidizing agent? Okay. Well, the agents are the things that cause the other thing to happen. So let me say this. Carbon oxidized, clearly. What caused the carbon to oxidize? The oxygen. So the oxygen would be the oxidizing agent. By the way, this is where the word oxidation comes from, because anything that reacts with oxygen is going to oxidize. Okay? So the oxygen is the oxidizing agent because it caused carbon to oxidize. The carbon, on the other hand, is the reducing agent because it caused oxygen to reduce. Now, usually what the technical way of doing this is, it's not so much the carbon, it's the methane. If the methane had not been there, it's the substance that has that element is going to be the agent. So the methane is the reducing agent. The oxygen gas is the oxidizing agent. I'm just telling you this. This is bonus material because AP no longer uses the terminology or tests you on the terminology. But you will see this in the rest of your lifetime if you continue taking some chemistry classes. All right. Let's move on and go through some examples of balancing some equations using the idea of oxidation and reduction. First, one of the first things we have to do is determine whether we're actually dealing with a redox reaction. I know. Okay. We didn't balance it yet. I let that one go. We're going to use... We didn't balance that. Okay? We can go back to that one maybe here in a little bit. Actually, as I'll probably have you go back and do that when using the oxidation states method. Okay? But anyway, so like I said, one of the first things we need to do is identify whether a reaction is a redox reaction or not. And so we do that by assigning oxidation numbers to all the elements and finding out if any of the oxidation states change. So please take a moment and assign oxidation states to each of these elements if you haven't done so already. Mr. Homan was trying to wave to me, but he couldn't see me through all the stickers. What are those called? Window clings, sorry. They are sticking to the window. Clinging to the... So there's a distinction between stick and cling. Clinging is what I see young people doing out in the hall. Sticking is... So Christina, let's go through and do some oxidation states. Sodium, nitrogen, oxygen, calcium, oxygen, hydrogen, sodium, oxygen, hydrogen, calcium, nitrogen, oxygen. Is this a redox reaction?
No.
Why not?
Nothing
Nothing changed. What type of reaction is this? Double replacement. I'm just showing you. They're not all going to be redox, and you are going to have to be able to make that distinction. There's our first one. We can just balance this the way we normally balance it. Boom, boom. Just by inspection. Balancing by inspection. Bless you. All right. Now let's get real. I just had to do that because I think you guys are used to, like in many of your classes, you learn a topic. That's the only thing you worry about is that topic. And again, in chemistry, what's the rule? You got to know everything all the time. All right. Now, given 14.2 grams, sorry, we'll do that here shortly enough. All right. There are two methods that we can use to balance chemical redox reactions. The first one is called the oxidation states method. Okay, and this, well, in both methods, we're going to use the change in oxidation state to help us determine how to balance it. The first method I'm going to show you here, either method can be used for any redox reaction. It's just that the other method that I haven't shown you yet is really useful for really, really complicated reactions. This one is going to be able to be used for almost everything that you will run into in AP. Why is that hot? Ah, that's why. Camera's accidentally on. It's really hot. Okay. Here we go. Let's look through our first example. First example of oxidation states method. By the way, the states of matter are typically pretty important on this. You'll see why later. Whoa, did I do that right? Yes. Okay, once again, let's find out if this is a redox reaction by assigning oxidation states to all of the elements in each of these substances, the species involved. Okay. Oxygen. -2 each, which means the manganese is +4. Aluminum. Manganese. Aluminum. And the oxygen. -2 each. So, is this a redox reaction? Did the oxidation states change? Yes. Doesn't matter which one you pick first. Pick an element of a that changed its oxidation state. Aluminum. Aluminum did what? Oxidized by 3 electrons. Each aluminum atom oxidized by 3 electrons. Can you guys see that? Okay. What reduced? The manganese reduced by 4 electrons. We're going to use that information. We have to equalize the electron transfer. So what we're going to do is look for the lowest common multiple of 3 and 4. That would be 12. So somehow or other we have to get the manganese to transfer 12 electrons from here to here. I would do that by multiplying that by 3. Somehow or other I have to get the aluminum to transfer, or in this case, lose 12 electrons. I would have to multiply the aluminums by 4 in order for that to happen. Would you guys agree? So we have now equalized the electron transfer. The manganese have gained 12 electrons. The aluminums have lost 12 electrons. We have taken care of those electrons. Yes?
So doesn't a 2 need to be in front of that last aluminum too? Since there's 2?
Ah, thank you. And there's a little thing that you guys have to be careful of. Because that would have actually been 8 aluminums. Would you agree? Which means that would be, what was it, 3? That'd be 24 electrons. So, Ms. Travis is exactly right. So be careful on that one. Now all we have to do is balance everything else. It's already balanced. We're done. And you guys may remember that from balancing equations back in the first time you took chemistry. Remember I suggested to you that to save oxygens for last because a lot of times they'll take care of themselves. And in this case, that would be true. So what do you think? That's a pretty nifty little method, isn't it? Now, could you have done it the old way? Absolutely. And somewhat quickly. But this is, you're going to find, will work out for some that aren't as obvious. Can I move on? Any questions? Okay, now, they can get a little bit more complicated, obviously. So, let's try this one on for size. I forgot to do the check. You know, we'll go back and do the check after we get this one done, because this will be a great opportunity to introduce the check, and then we'll go back and apply it to the other one. I forgot something. All right, anyway, what does this appear to be? How would we classify the way this equation is written up here? I disagree with that. If anything, it's a double replacement, but it's not even that.
Acid-base.
No, oh gosh, no. How did this get here?
There's something else. There's spectator.
Right. How did this get here? Ah, there we go. Thank you. It's a net ionic equation. You guys seeing that? No. You'll find out why here in a second. Okay. Because the spectator ions don't change their oxidation state. Remember we talked about that? The sodium stay sodium ions, the chloride ions stay chloride ions. They don't change. So we don't care about those. In this case, though, well, let's find out. If you haven't already done so, please assign oxidation states to all those elements. So how far are we? You don't even have a bookmark.
No, I don't.
You just, that's kind of what I do. Do you just kind of remember the page you're on?
No, I
Ish?
remember them.
Oh, I kind of remember the page.
No.
Near.
Around,
Yeah, and then you can kind of skim through and find out real quick.
But if you skim it, then you like do something you're not supposed to do yet, or like you forgot to do yet.
Yeah, skimming, I don't, yeah, it's okay. Hey, I don't know what this is about, so you like the suspense, don't you?
Like you can be like at this point, and then be like, oh, this character died.
Okay, here we go. Manganese ion.
Oh, I got this.
The manganese 2 ion. 2 plus. Anything here? Oxygens are -2 each, therefore the bismuth is +5. Over here, the oxygens are -2 each, therefore the manganese is +7. The bismuth is +3. Bismuth ion. There we go. Is this a redox reaction? Oxidation states changed. Okay. How did they change? Well, the manganese did what? Oxidized by 5 electrons, whereas the bismuth reduced by 2 electrons. So we're looking for the lowest common multiple of 2 and 5, which everyone knows is 10. So we need to get 10 electrons transferred. This is a starting point. It may not be the ending point. It's often the ending point. Okay? But this point here of trying to find the lowest common multiple will usually work. So I'm going to have to multiply the manganese by 2. Since they change by 5 electrons, if that process happens twice, that's 10 electrons. Whereas the bismuth, we're going to have to multiply by 5, because each of those bismuths transfers 2 electrons each time. If that happens 5 times, that's 10 electrons.
Do you multiply it by what is oxidized? Like it,
No, not necessarily.
Not like, but what I'm saying is like 5 times. What it's saying is like you multiply the Mn by 2 because it's oxidized by 5.
And again, that can get you into a trap sometimes. And this is why I'm trying to emphasize that this is a starting point, and we try to find the lowest common multiple.
Like it.
I know you get that, okay? You just need to do a bunch of these before you see where I'm going. Now, we now have the electrons taken care of clearly. I think that's why we did that. Now what do we have to deal with? Oh, I haven't done that yet. You're right. Now what do we have to deal with? The oxygens. Okay, so how many oxygens on this side of the equation? 15. How many on this side of the equation? 8. Uh-oh. Well, I hope you have an idea. Well, how can I add water? You can't add water to something that's not there. It's an aqueous solution, so it's already present. You've always been told, back when you were a freshman, whenever it was you learned about a balanced equation, that you can't add something to an equation to balance it unless it's present. And in this case, water is everywhere. It's like the poem, water, water everywhere. There is. You guys don't know that one? Rhyme of the Ancient Mariner? You guys don't know that? What are they doing in English classes these days? So, how many water molecules need to be added? Where? To the product side. We're in chemistry now. Product side. So we're going to add 7 water molecules over here. Great. Oh, wait. Now we got a bunch of hydrogens that weren't there before. Now I forgot to tell you something. Actually, I didn't forget to tell you. No. This reaction is only going to work if it is in acidic solution. What does an acidic solution supply? Hydrogen ions. So, whenever you're going to balance one of these things, you will often be told that it's either an acidic solution or basic solution. In this particular one, it's an acidic solution. So that means hydrogen ions already floating around in there, okay? And which side needs a hydrogen ion? The reactant. Excellent. The reactant side, and how many does it need? 14 hydrogen ions. Please do not forget to write the charges. Some of you have already seen me get on your cases a little bit about not writing charges when you're writing things out. This is precisely why. Because it's going to matter here in about 8 seconds or so. So now, do we have all the atoms balanced? Yeah, we kind of made sure that they got balanced. I mean, we physically manipulated the thing to make sure they balanced. All of these species are present. The water's already in there because it's an aqueous solution. It's an acidic solution, so there's hydrogen ion there also. The next thing we do, though, and I forgot to have you do this on the other one. It was kind of a no-brainer, but you have to make sure your charge balances. So what we do is find the net charge on each side of the equation, or the total charge on each side of the equation, and make sure that it balances. So what is the charge of everything on the reactant side? Yeah, we have 14 positive charges here, 5 negative charges here for a plus. Yeah, I messed up. 18. And then we have 5 negative charges, which is a plus 13. Over here we have 15 positives and 2 negatives, so a plus 13. The reason I think this is a really good idea for you guys to get in the habit of doing is I'm telling you, and as you can imagine, in the course of an AP exam, when your brain's going 1,000 different directions, and you get a little flustered once in a while, you make a small mistake here and there. This is a good way to check to see if you balance everything out correctly. So, just saying. So check the charge too. By the way, if we look back at the previous example, which I erased, does the charge balance? Well, there were no ions in that one, so it's pretty obvious. Would you agree? Awesome. Why don't you guys take a moment? Not that this is really difficult, but it's a good way to test your ability to do this. The original equation we looked at, the methane plus oxygen, we've already determined by how much everything oxidized or reduced, I think, didn't we? Yeah. The carbon oxidized by 8, so on and so forth. Use that information to help you balance the equation. And keep in mind that I'm saying that this oxidation states method is a great starting point. You may have to go further from there, but I'm just saying, you know, we use that lowest common multiple thing now, which is what? 16? Well, that seems to be a little bit of overkill, doesn't it? Remember what the goal is to get the electron transfer to balance. So this one carbon right here is losing 8 electrons. Therefore, all of the oxygen somehow has to account for 8 electrons. Well, each of these oxygens would end up being a -2, right? To get to 8, don't I have to have that happening 4 times? So I'm going to multiply this by 2. And if I multiply that by 2, I've already got 2 over here. That do it? So again, I'm saying that lowest common multiple is a good starting point, but sometimes it's not enough. You have to go further. Sometimes it's too much. You actually have to think about the number of electrons that are being transferred. Okay, this is the oxidation states method. In my opinion, this is the preferable way for you guys to balance redox reactions on the AP exam because it's quick, it's easy, it doesn't take much time. However, there is another way. And this is called the half reaction method. And this is where... How much time do I have? Oh, then I've got plenty of time. Emily and Gracie. You guys probably can't see that. Can you see it? Well, I know, and that's going to be hard. Here's what I'll do. going to be too big.
Yeah. If you go to the left one, you can see it.
There we go. Yeah, this is going to work. You just can't see it all. Okay, so this is the half reaction method. We're going to learn how to do this in both acidic solution and basic solution. It is, in my opinion, the easiest way to teach this stuff is doing the acidic solution first, because the basic solution essentially only adds like 1.5 more steps at a certain point. So if you know the acidic solution, the basic solution just requires like a minor adjustment to it. And it will make so much sense when we get to it. So anyway, here are these steps. Now, this is where you, being the intelligent people that you are going to screw things up. Because you, as the intelligent people that you are, have a tendency to get things and grasp things and then start skipping steps. Oh, well, if this is true, then blah, 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 blah. You cannot skip any of these steps. Everything has to be done in the order that it's presented. You can't skip steps, Joe. Just trying to help. All right, so here we go. Let's look at this reaction. Our old friend permanganate. Okay. Once again, how is the information being presented? What form? It's a net ionic equation. Okay, we're leaving out the spectator ions. This could be sodium, it could be potassium, this could be nitrate, sodium, potassium, doesn't matter. Is this a redox reaction? How do you know? You have to find out if any of the oxidation states changed. So by now you guys know that this oxygen is going to be -2 each, therefore the manganese is going to be +7. You guys will learn really soon that manganese and permanganate is +7. Obviously the iron 2 is +2. The iron 3 is +3, and the manganese is +2. Honestly, you guys on an AP exam, I would hope, would choose to use the oxidation states method. However, I'm using a relatively easy one to teach you the half reaction method. Okay, so here we go. We've done step 1. Would you agree? Great. Pick one. It doesn't matter. Which species do you guys want to go, oxidized or reduced? Reduced. Excellent. Usually people go oxidized, so this is awesome. You guys are going the other way. It doesn't matter. What species reduced? The manganese reduced, right? So we are going to write the species that were involved in the reduction. Here's a hint to you. Put a line in the middle of your paper, middle width-wise. Because what we're going to do is grow the equation on each side of that line. So if you put it in the middle, you've got a chance of not running out of room. Now, what were the species involved in the reduction? Permanganate and manganese 2 ion. So there, we wrote the half reaction. Well, I work with each one separately, as you can see. We're going to come back and apply all these steps to the oxidation one here in a second. So next, balance each atom other than oxygen and hydrogen. This should sound familiar from other things. So what are the elements other than oxygen or hydrogen? Manganese. Are they balanced? Yes. Moving on. Balance oxygen by adding water to the appropriate side. Well, we've already experienced this. Do we need to add water? Yes. And to which side do we need to add water? To the product side. And how many do we need to add? Excellent. Now we're going to balance hydrogen by adding hydrogen ion to the appropriate side, in which case it's going to be the reactant side. And how many are we going to add? We're going to add 8. Awesome. Now we are going to balance the charge by adding electrons to the appropriate side. Well, on the reactant side, what is my net charge? +7. On the product side, what is my net charge? +2. So we have a deficiency of electrons on the product side. I need to add 5 electrons. Net charge of +7, net charge of +2. No, you can't put them there. They have to be over there. Well, literally unwrite that in pen. Are you with me now? There we go. Yes? Because remember, the electrons are being transferred. In the previous stuff that we did, we just assumed it was happening all within the system. What we're doing now is splitting the system in half. This will make a really lot of sense when we get to chapter 19 when we make batteries. Okay, this is what goes on in a battery. I know that. So anyway, is everyone comfortable with what we've done so far? Well, yeah, because we had an excess of positive charge, so I have to make, yeah. Okay, next, let's do the same thing for the oxidation half. And what's involved in the oxidation half? Fe and Fe. So now, Joe, you can't skip steps, so balance everything other than oxygen and hydrogen. Done. Balance oxygen. Done. Balance hydrogen. Done. Balance the charge by adding electrons to the appropriate side. Yep, 1 electron on the product side. Now I want to point something out. We should have known that it's going to have to be on the product side because the other one was on the reactant side. They're never going to be on the same side. If you ever run into a scenario where you've got your electrons being on the same sides, you screwed up somewhere. This method is easy. It's really easy. You can't screw it up until you screw it up. And you guys will find the tiniest little places to screw up. You won't write down the charge on an ion or something like that. You'll forget to distribute a number through as you're multiplying things. There are tiny, tiny little places that you can screw up. Other than that, it's really, really easy. All right, then here's the key. This is exactly the same thing as the oxidation states, except we're doing it in 2 separate reactions. We need to balance the charge, the electron transfer. Sorry about that. We have to equalize or balance the electron transfer by multiplying the appropriate reaction by the necessary coefficient. Sometimes you need each of the reactions to be multiplied by a coefficient. In this case, we're going to have to multiply the oxidation. Yep. Now remember, this was here. This was the reduction. Here was the oxidation. In this case, we're going to have to multiply the oxidation by 5 electrons. So everything within there gets multiplied by 5 electrons. And at this point, you just add up the reactions. This is a technique we're going to use in like 3 different scenarios in this class. There's like 3 different concepts that basically have us add a bunch of reactions together. So we just add everything up. Does not matter to me how you do that.
Question.
Yeah.
When we're adding them up, can we, like, instead of writing the 5 electrons on one side and the 1 electron on the other, can we put 4 electrons on one side and 7 on the other?
No, you can't do that because watch this. Well, that's what the whole point was. That's what the point was. That's why we did that. So we're not going to write any electrons down. So, and like I said before, it doesn't matter. I don't care how you do this. I'm going to walk through a way, but you guys do it any way you want. Yes?
So if that one electron was like a 3,
Yes, and the other one by 5. It's exactly the same thing we did with the oxidation states. So, here we go. I'll just start writing everything down. Boom, boom. Next. Make sure everything gets accounted for. Yes?
Can you still multiply the bottom part by 5?
Yeah, again, you distribute that 5 throughout everything inside the parentheses there. And Gracie, I'll give you that opportunity really, really soon to do what you were asking about. Okay. Now, at this point in time, that was a lot of work, right? A lot of little places to make mistakes, so obviously what you should do is go back and confirm that not only that your atoms balance, but your charge balances. How many hydrogens on this side?
8.
How many over here? 8. How many manganese? 1. 1. How many oxygens? 4. 4. 5 iron. 5 iron. What's my net charge on the reactant side? 10, 18. Plus 17, you said? Yes, I agree. And what is the net charge over here? Plus 17. Give yourselves a little round of applause for balancing your first half reaction method in acidic solution. Can't screw it up. Okay. Let's try one on your own. You guys did really well with that. Whoops. Oops. I'm getting a little old. All right, here we go. It was. Thank you, Joe. Whoa. Can you do it? It's actually from a movie, but you guys wouldn't know about it. You have to. Yeah. No, actually, it's Can You Dig It? But you guys know that movie? How do you know that movie? That's not how it's said. What's the movie? Warriors?
Yes, yes.
You know that movie.
I swear to God, the part where he goes, where the chick
Yeah,
and he goes,
yeah.
Warriors, and I was like, yeah.
You have good parents.
No, I don't.
You have good parents.
I'm just kidding, I love Jessica Jones.
Do you know who the star was in that movie?
No.
Precisely no one. Nobody that anybody has ever heard of in their entire lives. Came out in like 1980. How do you know that?
My brother was, because he thought that was so funny.
It is.
And so we just had to watch it over and over. Was it scary?
No.
That was scary. Yes, that is terrifying.
So you know the movie. Can you dig it? That's how it's said. You know that movie too.
Yeah, I didn't remember what it was called, but I remember.
You need. I need to make like a little sound clip of that, and whenever it does something, I should press that. Can you? That's a, yeah. Oh, a button. Thank you. Is this a redox reaction?
Yeah.
Very good. My group did not get to this last year, mainly because of the whole debacle of moving from there to here. Yeah, oh, it was a debacle. Just 3? I use a lot of words, Judy. I like words. I like words. I do. 3 times. Yes. Well, no, it's about all the gangs in New York City. Yes. And then another gang is chasing them. No, it's pretty good. Why? Scary? I know. Oh, it's a very entertaining. If you're a teenage guy, it's a very entertaining movie. If you're a teenage guy in 1980, it was a very entertaining movie.
Didn't they say this wasn't scripted though? They said that part wasn't scripted.
I don't know, but that part
With the bottles, he's like, that part wasn't scripted.
How you doing there, Gracie? Which one oxidized?
The copper.
Yes, it did.
Wait, wasn't that one? Oh yeah, never mind.
Okay.
Don't worry about it.
Okay, based on this, the nitrogen reduced. Just to show that it doesn't matter, I think the last time we did the reduction first, this time I'm going to do the oxidation first. It does not matter. Clearly the copper is what oxidized. So we balance all the atoms except for oxygen and nitrogen, or sorry about that, oxygen and hydrogen. Clearly they balance. That is a place that you will occasionally make a mistake. If we had like Fe2O3 or something like that, you guys may forget to balance the the ions. Anyway, then we balance the oxygen by adding water. Done. Balance the hydrogen by adding hydrogen ion. Done. Balance the charge by adding electrons. Yep. Okay, move on to the reduction, which would include the materials in the nitric acid. Balance everything, or balance the everything except oxygen and hydrogen. Done. Balance the oxygen by adding water to the product side. Balance the hydrogen by adding hydrogen ion. I don't know what I used last time. Red. How many hydrogens am I going to add? Good. And lastly, balance the charge. You betcha. That's pretty darn easy, isn't it? Now what are we going? We have to equalize the electron transfer. We're going to multiply the top equation by 3 and the bottom equation by 2. That clearly eliminates our electrons. That was the whole point of that step. And now we just distribute through, add everything up, blah, 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 blah. Who's saying that? Is that Gracie? All right. Whoa. I mean, you clearly don't have any idea how this relates to the other stuff we're going to do yet this year, but this is a really good technique to help us with that process in the other two concepts that we're essentially going to add up two or more reactions together. The only thing that we're kind of doing it is combining terms right now. When we get to the basic reaction, that's when we're really going to have to looking at combining terms that show up on each side of the equation. Yes. Yeah, I just didn't do that real quick because. No, I mean, yeah. Okay. No, that's awesome. I'm glad you did that. There we go. Now, do the atoms balance. 8 hydrogen, 8 hydrogen. 2 nitrogen, 2 nitrogen. 6 oxygen, 6 oxygen, 3 copper, 3 copper. Does the charge balance? We have a +6 here and a +6 here. Any questions? 7 minutes or 5? No. Well, yes. 0. I think we've covered that one. So now we're going to look at the half reaction method in basic solution. What I'm going to do is give you guys a reaction. And since it's incredibly similar to the acidic method, what I'm going to do is have you balance it to a certain point in the acidic solution and stop. That way you guys get a little bit of practice with that. So the reaction we're going to look at is yeah, I'll get that up there. Don't worry. Okay, now, I know that I'm writing the word base up there. There are numerous ways for me and or the AP to indicate to you whether it's acidic or basic. This is one of the ways. Now, what I would like you to do is balance this as if it were in acidic solution up to the point that you add hydrogen ion for both reactions. You guys clear what I'm saying? Balance it as if it were in acidic up to the point where you added the hydrogen ion. Do that for both reactions, and then I'll show you what to do from there. I just wanted to make sure it was still recording. Bless you.
I actually would prefer if that screen was up on that. You can watch you record yourself. It keeps me more interested if it makes you feel any better.
Do you like edit these and make sure that nothing stupid is said before you put them on?
Used to. Not any longer.
When did that stop?
2 years ago. I know. Did you stop at the acidic? Did you stop at adding hydrogen ion?
No, I haven't even gotten there yet. I was last. I'm working on it.
You did water before hydrogen, right? Or is that hydrogen?
Whoa, that was dumb. Okay, this is the point where I asked you to stop. Now, here's why we stopped here. Currently, each of those reactions appears to be in acidic solution because there's a bunch of extra hydrogen ion floating around. Would you agree? Okay. However, I've already indicated to you that this is to be balanced in basic solution. So what we need to do is neutralize the acid. How do we neutralize? With some what? With some what? Hydroxide. So, now, here's the basic method, the instructions for it. This is all in your book, okay? But anyway, all of this is exactly the same as what we had just gotten done doing. The difference is right here. We balance the hydrogen by adding hydrogen ion to the appropriate side, right? But now to neutralize the hydrogen ion, we have to add the appropriate amount of hydroxide ion, and just like in algebra, whatever you add to one side of the equation, you have to add to the other side of the equation. So what we're going to do is add 4 hydroxides to this equation to neutralize that hydrogen, but we also have to add 4 hydroxides here. Would you guys agree? Over here, we're going to add 14 hydroxide ions, which means over here we're also going to add 14 hydroxide ions. Now we've got an interesting scenario. Well, now we're going to look at the charge and balance the electrons, same as before. So I've only added one step to your life so far. Yes, thank you, Judy, but we'll get to there here in a second. Let's do the electrons first. Negative over here, -4, -1 over here. So we need 3 negatives over here, 3 electrons here. Over here we have a -8 net. Over here we have a -2 net. Therefore, 6 electrons over here. So what am I going to have to do? Multiply the top one by 2 to get 6. Hold on. Everything else stays the same, but Judy already picked this out, and this is where it gets a little interesting. What if we just created here? Water. What if we created here? Water. We have got water everywhere. Boom, 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 boom. You need to find your net number of water molecules. You only want water showing up one time in the final equation. Same thing with hydroxide. We've got hydroxide here, we've got hydroxide here. The hydroxide is only going to show up one time in the equation, so you have to find your net hydroxide. Yeah, there are 4 negative charges here, and there... You knew that. Hey, you guys did a great job today.
So do you have our quizzes from last time ready already?